This is May-June 2021, paper 42. May-June 2021, paper 42. Okay, so let's start with this paper. Define gravitational field strength. We know this is force per unit mass, which is the value of G, which is Newton per kg, or as meters per second square. But since he's referring to as field strength, we will refer to this as this one. If it had said gravitational acceleration, then we would have referred to this unit. So an isolated planet in uniform sphere, radius this, mass this, may be considered to be a point mass, rotating at a period of 24.6 hours. At the equator, calculate the up to 3 significant figures field strength. So the formula is very simple. The formula is G equals to Gm over r square. So simply replace the values as 6.67 into 10 raised to the power minus 11 into the mass of the object is given to you as 6.4 to the power 23. And divide this with r square, which is 3.39 into 10 raised to the power 6 meters whole square. Don't forget to take the square. This will come out as 3.7 to 6 meters per second square. This looks like Mars. Yeah. So this is going to be 3.73. He said 3 significant figures, so we have to oblige. The centripetal acceleration, which is going to be A equals to V square over R, or it could have been omega square R as this one. Since we don't have the centripetal, since we don't have the tangential velocity, and we do have the time period mentioned, so I believe that we are going to use R omega square. So this is going to be simply 3.39 into 10 raised to the power 6, the radius, into 2 pi divided by 24.6 hours multiplied by 60 minutes multiplied by 60 seconds. And this has to be squared. Don't forget the square. So this is going to come out as 0.0171 radians per second, which is going to be 0.0171 up to, basically this was 706, which became 171. The force per unit mass exerted on the planet by the surface of the planet. This is an interesting question. You see, in terms of the surface of the planet, the normal reaction is in the upward direction and the force of gravity is in the downward direction, right? And this is the normal reaction. Now, the centripetal force is exerted because of the resultant of the two forces, right? So force of gravity, which is weight minus the normal reaction, which is in the upward direction, is going to cause the centripetal force. So let's replace them with the respective formula. So I understand that this is going to be mg as weight minus the normal reaction, which is generally equal to mg, but since centripetal force, since they are being rotated, centripetal force is involved. So some of the force is also the responsibility of centripetal force, right? So let's call this as ma, acceleration due to the normal reaction because of this direction of force. Okay, all right. Equals to centripetal force, which is mv square over r, which you just calculated in the previous part. Now we can see that the mass gets cancelled out from the whole equation. What we are left with is simple 9.81 minus, sorry, not 9.81, but the gravitational field strength of this planet was 3.73. So 3.73. And since we're supposed to find out the force per unit mass on the surface of the planet, so we're going to take the normal reaction onto this side and bring this over this side. What has the planet, or what does the planet have to provide in order to compensate or to act against the weight while the centripetal force exists? So let's bring centripetal force over here. So the answer of this v square over r was already found as 0.0171. So this, while coming on this side, will become negative. So 0.07171 equals to the centripetal acceleration, or at least force per unit mass due to the normal reaction. So when you subtract this, this comes out as 3.71. This comes out 3.71. So this is what's actually happening. The resultant of the gravity and normal reaction produce the centripetal force. Okay, all right. So because the Earth is moving, right, the normal reaction will be slightly less than the weight of the object, because some of it is being provided by the centripetal force. Anyways, so we have an ideal gas equation system, PV equals to nRT. Very simple and straightforward. No need to waste our time. So he says show that the number of molecules. So I need to calculate the number of moles, and then I can use it to calculate the number of atoms. So I can use PV equals to nRT. So pressure was 8.5 into 10 raised to the power 5. Volume is 3.1 into 10 raised to the power minus 3. And we don't know. Gas constant is 8.31. Temperature is 290. Already given as Kelvin in the initial situation. So when you find moles, they're going to come out as 1.093. Multiplying this with Avogadro's constant, power 23. This is 23, we get 6.58 into 10 raised to the power 23, which is, of course, up to two significant figures, 6.6 power 23 atoms. So we've shown what the examiner wanted us to show. Show that the final temperature is 190. So what has happened? A few physical changes have taken place because of this. And let's compare the two situations. We have PV equals to nRT. What factors are changing and what is not? You see, N and R are not changing in both situations. The number of moles and the universal gas constant are exactly the same. They are not changing. So what are we left with? We are left with an equation that PV is proportional to T, which will be applicable for this one, and PV is proportional to T, which is applicable for this one. Since both of them are equal to NR, or have a constant combination of NR, I can compare them. I have two ways to do this. So let's apply PV divided by T. How did we do that? By bringing T over there and equating this to NR. This is also NR, this is also equal to NR, bringing T over there. So two situations can be compared. So PV divided by T is equal to PV divided by T. So these are the pressure and volume for the first situation, which is simply 8.5 into 10 raised to the power 6. Sorry, it's 5 multiplied by volume, which is 3.1 into 10 raised to the power minus 5 divided by temperature, which is 290, equals to the pressure of the second situation, which is 6.3 into 10 raised to the power minus 3 into 2.7 into 10 raised to the power 5 divided by T, which is TF, which we didn't know, which is this one. Okay, so TF can be found by this method as TF equals to 187 point something, which would be rounded off to 190 Kelvin because of this. Okay. The other method was to use the equation PV equals to NKT. Now, since the number of atoms are exactly going to be the same, we can find the temperature for the new situation by simply using the second scenario in this, right? So it would have been 6.3, simply 6.3 into 10 raised to the power minus 3, the volume, the pressure was 2.7 into 10 raised to the power 5 equals to number of atoms is 6.6 into 10 raised to the power 23. And Boltzmann constant is 1.38 into 10 raised to the power minus 23. And find the final temperature. This would also have given you the answer of 190 Kelvin. So either use the mathematics or either use the state equation. That's up to your choice. Your choosing. Okay, part number 2. We know this equation. He says calculate the increase in internal energy of the gas, and K is the Boltzmann constant. So simply put, we have 3 by 2 K, which is 1.38 into 10 raised to the power minus 23. And this T is the delta T, or the change in energy. So it changed from the final temperature is 190 and the initial temperature is 290. So when you calculate this, this comes out as 2.07 into 10 raised to the power minus 21 joules. Now this is because of just one atom, right? We have how many atoms? We have 6.6 into 10 raised to the power 23 atoms. When you do that, you're going to get 1366 joules, which is roughly going to translate to 1400 joules, right? So now we need to realize what we have done with the system. What have we done? So the volume has increased, the pressure has decreased. So by the looks of it, according to the first law of thermodynamics, let's write down delta U equals to Q plus W. So what you've done, it looks like the temperature reduced from 290 to 190. And by the looks of W, since you've allowed the gas to expand, this will actually be minus 1400 joules because you've taken energy out of the system, right? So by this method, due to the change in temperature, this Q is decreasing, so delta U should also be decreasing. So this is going to be actually negative 1400, or the change is negative 1400. आपने इसमें से एनर्जी निकाल ली है, तो जो चेंज है यानी इनिशियल और फाइनल का जो डिफरेंस है उसमें 1400 आज कम हो चुके होंगे. They would have been reduced in comparison to previous situation, compared to today, compared to the latest situation. 1400 is the deficit because of the change of temperature. He says use first law again. Y external work done W on the gas during the expansion is equal to the increase in internal energy. So to explain this, we need to write down delta U equals to Q plus W. So since he mentions in the question that there is no thermal energy exchange, right? There is mentioned in the question somewhere over here, there is no thermal energy transfer. That means that in our situation, Q was equal to 0. It did not participate in the system. So delta U only comes down to the work done, which is P delta V of the gas, right? So no thermal energy transfer he mentioned in the question. So that's why all the internal energy change is dependent on the work done. ठीक है? और इसमें जो टेम्परेचर कम होता हुआ नजर आ रहा है ना, वो प्राइमरीली इसलिए हो रहा है बिकॉज आपने इसमें से एनर्जी निकाली है, आपने वॉल्यूम बढ़ाया, आपने एक्सपेंशन की परमिशन दी. गैस एक्सपैंड सिर्फ तभी कर सकती है जब आप उसको वर्क टन के लिए एनर्जी दे दें. और गैस ने वो एनर्जी ली कहाँ से है? सिस्टम से. सिस्टम के पास सरप्लस पड़ी हुई थी, उसने उससे एनर्जी ली और एटमॉस्फेरिक प्रेशर के अगेंस्ट पुश अगेंस्ट किया, वर्क डन किया, तो वो एनर्जी अब उस सिस्टम में से माइनस होगी, खत्म होगी, क्योंकि वो तो इस्तेमाल हो चुकी है into doing work. Question number 3. The acceleration, okay, x, right? Explain how the expression shows that the liquid in the tube is undergoing simple harmonic motion. आपको कैसे पता चलेगा इस expression को देख के? सबसे पहले तो we need to realize that this is actually proportional to the displacement. ये SHM की underlying condition है. दूसरी बात, acceleration is proportional to negative displacement. ये SHM की दूसरी बात है, ठीक है? So let's discuss them in terms of simple statements. So और जो negative sign है ये बताता है कि ये दोनों opposite है. So acceleration and displacement are opposite. और ये बताया किसने? Negative sign ने. ये लिखना है आपने, ठीक है? The negative sign shows that. Then the acceleration is proportional to the displacement. So as far as you're going away from the mean position, your acceleration will increase. तो जितना mean position से दूर जाएंगे उतनी acceleration तेज हो जाएगी. Same thing applies for the pendulum case. From the mean position, if you're very far away, the angle theta increases. So the restoring force, which is mg sin theta, also increases. तो जितना आप दूर जाते जाएंगे उतनी restoring force ज़्यादा होती जाएगी, and hence acceleration बढ़ती जाएगी. And of course, इसमें we have a constant which is g by L is a constant. He says length L is this, determine the period t. So we have g by L equals to omega. So g divided by L equals to omega square. G is 9.81, length is 18 into 10 raised to the power minus 2 equals to 2 pi by t ka whole square. So t can be found algebraically 0.85 seconds. This question is a bit tricky, इस पे थोड़ा time लगेगा. He says that the loss is 6%. तो सिस्टम की एफिशिएंसी कितनी होगी? 94%. ओके, निकालनी एनर्जी है और हमारे पास एम्पलीट्यूड की बात हो रही है. खैर, एनीवेज लेट्स गो थ्रू दिस. सो एनर्जी ऑफ ऑसिलेशन और इवन दिस ऑसिलेशन is actually equal to kinetic energy, which is half mv square. Now when you put in the v square, that becomes half m omega square under root x naught square minus x square whole square. So this comes down to half m omega square into x naught square, which means that the energy, now these are all constants. So what does that mean? It means that the energy is proportional to x square or displacement square. Okay, So first we need to find out the amplitude or the displacement, then we can find out the ratio of energy at least. So the initial energy, let's take that initial energy as the x naught square. This was what it had at the beginning, and we're going to find the amplitude in terms of x naught as the current situation. So what's actually happening? So let's say you started off with 100% amplitude. This is the amplitude, right? So at the very beginning, the amplitude at this point was 100%. What is going to be the amplitude at this point? This will be 94%. So there is a loss of 6% when the second oscillation took place. Similarly, again, a loss of 6%. So if you look at the efficiency model from O levels and IGCSE and A levels first year, you're providing, let's say, I naught, or you're providing X naught of energy, right? So if it is 94% efficient, you get 0.94 times of I naught and 6% gets wasted. Now this is happening again and again, one by one. So you provided, at this situation, you provided 100%, you only got back 94. Now the next machine is also 94% efficient. So if you want to get the output of that, that will be 94% of this value. So that becomes 94 whole square. Then because we're going for third oscillation, 3 oscillations, there will be a further reduction in 6%. So this becomes 94% efficient. So 94% of this value becomes 0.94 whole square multiplied by 0.94, right? So this was actually looked upon as in terms of efficiency, but then it becomes easy that this is actually cube of the displacement. So first we figure out what is the displacement or what's the amplitude. If the original amplitude was x naught, what is the amplitude today? So that would have been 0.94 whole cube x cube, or at least the x of that, right? No, not x cube, it would have been simply x. Yeah. So what does that become? It becomes 0.83 times x naught, which means that this is approximately 0.83 x naught. If this was, let's say, 5 centimeters, then this is actually 83% of that 5 centimeters. Now let's move on to the energy. We calculated that energy is the square of the amplitude of the displacement, right? So this will be 0.83 x naught whole square. So when you divide this, you get 0.83 whole square, x naught square cancels out. So you're left with 0.69% or terms of the energy. So it has lost approximately 31% of the energy as compared to before. Okay, 5a. Now electric potential graph is very simple. We have Q divided by 4 pi epsilon naught R. So V is inversely proportional to R. So if you take a graph of V ratio R, if R is 1, V is 1. If R is 2, V is 1 by 2, which is 0.5. If R is 3, V becomes 1 by 3, which is going to become 0.33. So on and so forth. If this is 4, then this becomes 0.25. We figured this out. Let's make this over here. So at R1, V is 1. At R2, it was 0.5 as this one. At R3, this was 1 over 3, so that became 0.33. So this will be somewhere along this line over here, 0.33. So then we make a graph line through them. So this is going to be very simple, like this one. But what about before 0? He says draw the graph from x0 to a 3. The potential inside the sphere is actually constant. If it had been a graph of electric field, that would have been 0 for electric field, and it would have been much steeper, because electric field graph is actually equal to Q by 4 pi epsilon naught R square, right? So its graph is actually being squared at every point. Now let's move on to this part. He says that lambda naught is the threshold wavelength which is required to eject the electron. And if lambda by 2 is being introduced, which is the high energetic photon, then the energy emitted by the photon, kinetic energy, is Emax. Now let's write down the function. The energy of the photon that is brought into the system is going to be equal to the work function plus the kinetic energy possessed by the photon, right? So photon energy is going to be HF, which is going to be equal to HF naught, the minimum threshold frequency that is required, right? Plus the kinetic energy. Now since the whole graph is in terms of lambda, let's replace lambda in this equation. So this is going to become HC by lambda equals to HC by lambda naught plus the kinetic energy. Now he told us that when the photon energy was lambda by 2, then the energy of kinetic energy was Emax. So let's replace this in this. So this is the photon energy. So if when it was hc lambda naught by 2 equals to hc lambda naught, which is its requirement, which it needs it, then the kinetic energy was actually Emax. Its value was Emax. So if I want to find out Emax in terms of lambda, then let's take this over other side. Algebraically speaking, this is going to become, this 2 will come up. This will become 2hc by lambda naught minus hc by lambda naught, which is coming from this side, equals to Emax. So what have we found? Emax is equal to hc by lambda naught, right? Okay. And we also know that if you provide just enough lambda naught, just enough energy from the photon, the kinetic energy, because this is the kinetic energy, is going to be 0, because the work function used all that energy and nothing was left for kinetic energy. So this coordinate will be 0. We understand that nothing will be left at the threshold wavelength or frequency. But lambda by 2, we realize that this is going to be Emax, kinetic energy of Emax. What will happen at lambda by 3? So again, the energy brought by photon going to be equal to work function plus the kinetic energy of the electron, ejected electron. This is hc by lambda. This lambda we will introduce this, equals to hc by lambda naught, which is its requirement for the electron ejection, plus the kinetic energy. This is what we're finding out. Let's move on to the lambda by 3 factor. So what if it was lambda by 3? So this was lambda naught by 3. 3 will go up. This becomes 3hc by lambda naught. This is still equal to hc by lambda plus the kinetic energy. So when this goes over there, this becomes 2hc by lambda naught minus hc by lambda naught. So this becomes 2hc by lambda naught equals to kinetic energy. Now we figured out in the previous part that Emax is equal to hc by lambda naught. So when you replace that hc by lambda naught with Emax, this becomes 2 times Emax. Simple algebra, right? So this equation, at this coordinate, this will be at this location. So we simply draw this at with a line that is going to look like this through the points. Okay, the only confusing part was this, that this had to be dealt in terms of algebra first. Then you will find out the kinetic energy, right? Don't try to draw the graph directly. Question number C. It decays and he wants you to draw the daughter particles up to from t equals to t to final t. Now, let's go back to O levels. Let's go back to IGCSE. We know that if we are looking at the parent, for example, and we are looking at the daughter particle, which is going to be formed, the total number of particles remain the same. So it's like an accounting problem again. Okay. So let's go through the parent, let's go through the daughter, and let's look at the total number of particles. The total number of particles remain the same, by the way, right? So since we have how many half-lives? We have, where is the half-life? Has he mentioned that? Yes. Yes, we can find it. Yes, we can see that the first half-life actually looks like this. The second half-life is actually going to look like this. So we can predict this, that the first time they get halved is actually this value. So this is t1 by 2, and this is going to be 2t1 by 2. So you figured that out. Okay, so let's start with 100. If let's say parents were 100%, the daughter was 0 at time t equals to 0. At the first half-life, the parents reduce to half, so they become 50. But where are the rest of the 50 particles? So the 50 get added together into the daughter particle, so they become 50. Or in short, this is n by 2, so daughter becomes n by 2. Now in the next half-life, we realize that half of the remaining parents will also come by. So these are going to become 25. This will become n naught by 4. This is my second half-life. Now where are those 25 particles going? First, there were 50 particles, right? So those 25 particles are going to become a part of the daughter. So they become 75, or you can say n by 2 plus n by 4. This becomes 3 by 4 n naught, right? Or you can simply say 0.75. No issues in that. Further reduction causes them to become 12.5, and those 12.5 are added in the daughter again. Now this becomes n naught by 8, or 8 times reduction. And of course, notice that at all times 100 plus 0 is 100, 50 plus 50 is 100. Total particle remain the same. 25 plus 75 is 100. 12.5, and what should be over here? So 75% plus 12.5% becomes 87.5%, which will again be 100%. But what will be this fraction? So this fraction will be 3 by 4 n naught plus n by 8, because only half of this was introduced. So this was only n over 8 introduced back into the situation. So this becomes 7 over 8 n naught. When you calculate this with a calculator, no need to worry. So this is n naught by 8, and this is 7 by 8 n naught. Now let's go back to the situation. So we have, this is going to be the third half-life. So I know that exactly at third half-life, they would have been n naught by 8. At the second half-life, they would have been n naught by 4. At the first half-life, they had been n naught by 2. So let's plot these graphs, let's plot these coordinates over here. What's happening? So after the first half-life, what happened? 50% of the parent decayed to become n by 2 and added those numbers to become for the daughter. So the daughter actually goes to this point. The daughter starts from 0 and attains 50% particles from the decay of the parent. Okay. Next, the parent has become to 25, or n by 4. So parent comes down to n by 4. The daughter gains n by 4 atoms and becomes 3 by 4n, or at least 75%. So that 75% is visible at this location, which is going to be 3 by 4 n naught. Okay. So at this point, this will be the coordinate. So the line continues to go to this point. Of course, you're going to draw the line at the end in one single stroke, but over here, we're going to compare this one coordinate by one coordinate to fully understand it. Now, what's happening by the third coordinate? You see, by the third coordinate, we get n by 8 and 7 by 8. When you calculate this fraction, this is going to look like 0.875, which is, of course, 87.5%. So by precisely calculating the number of atoms at that point, you're going to come to this point somewhere. So 87.5 at a certain height from the 0 axis. Count the number of boxes properly, okay? What to do with the last coordinate? You see, it told me that n number of atoms are still present. It started off with, let's say, 30,000. And it's probable, ho sakta hai ki today it has only 1500 atoms. So what are the current atoms, okay? So we need to count the number of boxes, that because we know that the total number of atoms in the system remain the same. So if they are n today, up to 4 boxes, if you zoom in, you will see that these are 4 boxes. You can see that on the paper as well. So it will end at less than 4 boxes at this location, because still some parent is left. Not all of it has become the daughter. So this is going to continue like this. So in terms of 100% accuracy, this is how it was supposed to be drawn. How to choose coordinates, how to look at them. Question number 6. He says, explain how the plates act as a capacitor. Very simple, very easy. You're going to create a hypothetical situation that if potential difference was applied, for example, if potential difference was applied across the plates, what will happen? A plate will have positive voltage and the other will have negative, and there will be an electric field established between them. So then you will say that energy is stored, or energy is stored how? In the form of either electric field, या तो electric field की form में होगी, या it is because of the separation of charges. Separation of charges on both plates, and this work has been done by the battery. बैटरी ने ही चार्जेस को सेपरेट किया है, जो कि अब दोनों प्लेट्स के ऊपर एक एक्सेस में है और एक के पास डेफिसिट में, and now the energy has been stored in the capacitor. That is how your mobile phone batteries, that is how your laptop battery actually functions. Okay. Again, a common question. He says, I can observe that he will first make it to go towards A, charge the capacitor, then move it to B. This is what he's going to do. But let's see what he does. You can pause the video at this point and read the question. Okay. So first he says, show that this can be done. Show that this is the proof. So we have the formula that is Q equals to CV, and we have the formula for current, which is I equals to Q by T. So let's replace this over here. So we get I equals to CV divided by T, and we know that frequency is equal to 1 over T as well. So I is simply equals to CVF. So I can figure out the current through the capacitor if I know the frequency, and if I know the capacitance, if I know the voltage. Let's go on to the next question. He says that the voltage is given, the frequency is given, the current is given, find out the capacitance. So we just have to plug in the values in the question given. So even if you were not able to make this proof, it's okay. You can still solve the next part. So don't lose hope in the middle of the question where you're solving it. Please make focus on the next question. It's okay. So I equals to CVF. Current is 2.5. Please make sure that you use proper the prefixes. 2.5 into 10 raised to the power minus 6 equals to capacitance is what we need to find out. Voltage is 180, which is given to us, and the frequency is 50 hertz given to us again. So C will be equal to 278 into 10 raised to the power minus 12 farads, which is going to become 280 picofarads minus 12. Oh, so minus 12, no need to write this down because pico is already written in the concept. You already likha hua, to aapko minus 12 nahi likhna padega. So the second capacitor is connected to circuit 6.2. The two capacitors are connected in parallel. They will be in parallel, even if he didn't tell me, they will be in parallel, because if the capacitor that is charged is connected across another capacitor that is even empty, they will transfer, or this charged capacitor will transfer energy to the second capacitor until their voltages become equal. Now, since their voltages have to become equal, this means that they are connected in parallel, because only in parallel the voltages become equal. State and explain the change in, if any, the average current in the ammeter. So this is going to decrease. Two capacitors okay, so two capacitors connected in parallel. It says now in this situation there is another capacitor connected over here. So what will happen? So I can see that the total capacitance increases, right? So due to current being proportional to CVF, capacitance increases, the current increases, while the voltage and frequency are constant. The current in the ammeter will be higher because you have stored more charge in it, right? Okay, and why the total capacitance increase? Because we understand that connecting them in parallel simply adds them together, C1 plus C2. If they had been connected in series, for example, like this, then this would have been 1 over C1 plus 1 over C2 is equal to 1 over C total. The overall capacitance would have reduced. But if the overall capacitance overall reduces every time, then why do we need to connect them in series? Basically, series connection are used to divide the voltage, to introduce a safety that the first capacitor or the second capacitor don't get high enough voltage in a certain scenario. Anyways, that's another issue. Magnetic flux density, we have already discussed this many times. You can memorize the definition of this magnetic flux density, which is going to be B equals to F divided by IL, which comes from F equals to ILB sine theta. So you make B the subject of the formula, you just describe what's what, okay? So B is equal to F divided by IL, so it is force per unit current per unit length. Simple. Okay, electrons have a mass of m, q, vacuum through potential difference V. He said derive an expression which mvq. Okay, no problem. So we have voltage defined as work done by a charge or work done on the charge, right? Depending upon you're looking at is EMF or potential difference. So since we're dealing with energy and speed, let's take Q over there. So this becomes small q divided and multiplied by V equals to the work done. And this work done will be translated into the kinetic energy, since we're dealing with speed, I believe, right? Accelerated in vacuum from rest. So yes, they're translating into kinetic energy. So I can see that kinetic energy is equal to half mv square. Now this equation becomes very clear and evident that charge multiplied by voltage is equal to half mv square. Since we want to develop a relationship, we can make V the subject of the formula for the final speed V. So V will be equal to under root of Q capital V divided by, 2 multiplied and divided by M. Okay, so this is velocity. Now, since you're using V as velocity and V as voltage, I will suggest you need to make this distinction clear for the examiner so that he knows which one is a smaller letter, which one is a larger letter. He's mentioned this examiner marking scheme many times that student need to write this clearly. Okay, so this is the situation. There is an electron. Okay, so electron is rotating in this direction. Okay, fine. And magnetic field direction, we don't know that yet, but that's not a part of the situation as well. He says, show that the Q by M specific charge is equal to this. Okay, no problem. We have already figured out from this scenario, we understand that the centripetal force which is causing this rotation is coming from the magnetic force. The magnetic force due to the Fleming's left-hand rule, of course. So we start with this logic that the centripetal force is equal to the magnetic force. So we come down to this mv squared divided by r equals to the magnetic force on a single charge is qvb. Now write this velocity in a fancy way to make it different from the other one. So we need to make q by m the subject of the formula. So let's replace them by that. So we can bring r over there. V cancels out. So we have q by m. So this would be m going to that side and b going to this side. So this becomes velocity divided by rb equals to q by m. So one side of the equation has looked familiar as I've successfully converted it into something familiar. Let's try to make the other side look like this again. So charge by mass is equal to velocity divided by br. And we understand that in the previous part, velocity was equal to 2qv divided by m. So let's take, since I can see that there is a b square and r square, I believe that there must have been, they might have taken a whole square on both sides. So let's take a whole square on both sides. Okay. So this is going to be square. This is going to be square. This becomes q squared divided by m square equals to v squared divided by b square r squared. I've successfully converted this, but I've lost q by m and I've lost velocity square as well. Now I can see that if I square this, the under root will go away. So this can be represented as, I think this makes more sense now. So this is going to be q mv divided by m divided by b square r square. I can see that this one q by m gets cancelled out. So q by m gets cancelled out by this q by m. Yes, now it makes sense. So q by m equals to 2v divided by b square r square. So we have made it successfully. We have shown what you wanted us to see. Again, if you're unable to show this part, you can still solve the next question. Please use this formula to solve this question. It says find the q by m of an electron. So charge by mass of an electron can be found by this formula, 2vb square r square. So 2 times what's the voltage it was accelerated to 30? What's the b? 0.38 millitesla. So 0.38 into 10 raised to the power minus 3 square. R square is 14 centimeters. So 14 into 10 raised to the power minus 2 whole square. When you finally calculate this in terms of algebra, this is going to become 1.625 into 10 raised to the power 11 coulombs per kg. That's a lot of charge. But that's a lot of electrons as well. 1 kg of electrons would have this much amount of coulombs. That's a lot of electrons. But anyways, so we can write this number over here. Okay, so he says suggest the arrangement outlined in 1 using the same values of b and v, not practical for determining q by m for alpha particle. What's the problem? You see, q by m, let's see this for electron. So this is going to be 1.6 into 10 raised to the power minus 90 divided by mass of electron, which is 9.11 into 10 raised to the power minus 31. This is for the beta particle or the electron. Let's do this for alpha for comparison. So alpha's charge is actually 2 protons. So it's going to be 2 times 1.6 into 10 raised to the power minus 19 divided by the mass is 4 times atomic mass unit, which is 1.66 into 10 raised to the power minus 27. Now there's a problem. For comparison, electron is already 2,000 times lighter. So this is not only 2,000 times heavier, this is on top of that 4 times even heavier than that because of the 2 protons and 2 neutrons. So what's happening? So since this is all equal to 2v divided by b square r square, he says what's the value of b and r? So b and r are exactly the same. B and v are same. So this actually comes down to inverse relationship with 1 over r. Now since the value of alpha's q by m is much smaller, because in terms of mathematics, this, whatever answer this may be, this will be much smaller in comparison to this. You can calculate this with the calculator. You will see that it's going to be much smaller. So if this is smaller, if Q by M is smaller, then R will be higher, which means that if you introduced an alpha particle under the same circumstances, its radius will be too high that it will cease to exist in this magnetic field. It will not be able to exist in this tiny space. So what we will write down, that Q by M of alpha is much lower. Hence, to maintain circular orbit, R will be higher, or for the circular R will be higher, which will be not existent inside that magnetic field, which is at least whatever R of the magnetic field is given to you, or whatever R is given for this path. It's not possible for the alpha particle because its Q by M is too small. So to compensate for that, we need to make a stronger magnetic field. We need to increase their speed so that we need to increase the voltage so that it stays there. This is a good question in terms of Fleming's left-hand rule and right-hand grip rule. But let's see. It says state two conditions, and this is very important. Charge particle के पास क्या होना चाहिए कि वो magnetic field experience करे, ठीक है? Does not experience a force. So जब तक positive charge या negative charge move नहीं करेगा, इसके इर्द-गिर्द magnetic field नहीं बनती. तो उसने भी यही कहा. It does not need to experience magnetic field. So charge should be stationary. So charge should be not moving. और अगर वो move कर ही रहा है, it should be moving parallel to the external magnetic field. क्या मतलब? For example, ये north pole है, ये साउथ पोल है. अभी तक हमने पढ़ा है कि करंट जो है वो ऐसे जाता है और नॉर्थ पोल इस तरह से, तो मैग्नेटिक फील्ड 90 डिग्रीज पे है. व्हाट इफ नॉर्थ पोल साउथ पोल इस डायरेक्शन में और आपने करंट भी इसी डायरेक्शन में मूव करवा दिया. सो व्हेन द करंट डायरेक्शन एंड द मैग्नेटिक फील्ड डायरेक्शन इज एग्जैक्टली द सेम, देयर विल बी नो force experience or no magnetic force. So this is what we mean by the second point. Positive direction हमें पता है, negative हमें पता है, ये बड़ी important बात है. So this is the direction of current. This is going to come back. So let's zoom in for, okay, so let's read the question first. He says, by reference to these magnetic fields, explain why the change in length of the spring, why there is a change in length of the spring, and state whether the spring extends or contract. वो कहता है change है या नहीं है, पहले वो बताएं. और अगर change है तो जो change अगर contraction का change है या repulsion का change है, उसके लिए हमें इसको zoom in करना पड़ेगा properly समझने के लिए. देखिए, बात को आपने 3 डायमेंशनली सोचना है और देखना पड़ेगा और से आपने, ठीक है? सो प्लीज होल्ड फॉर अ सेकेंड. तसल्ली से बात सुननी है आपने, और अगर आपको ना समझ आए, यू कैन वॉच दिस वीडियो अगेन एंड अगेन, यू कैन रिपीट दिस पॉइंट अगेन एंड अगेन. आई विल ट्राई टू मेक श्योर दैट वी अंडरस्टैंड दिस. सो सबसे पहले फर्स्ट वी नीड टू अंडरस्टैंड द डायरेक्शन ऑफ करंट. सो इन दिस कॉइल इट इज मूविंग इन दिस डायरेक्शन, फिर यहाँ से इस तरह से, एंड देन टुवर्ड्स दिस डायरेक्शन. सिमिलरली this direction, and this direction. So at least we can visualize how the current is actually flowing at every point. So I'm going to reduce, or I'm going to remove these points, but I'm going to only focus on these edges, because whatever is happening at this point will be happening along the line as well, because it's the same trend, right? So using the right-hand grip rule, what is the direction of magnetic field along this point? So if I was standing at this point, to my eyes, this current is actually moving away from me. This is current, right? So if the current is moving away from our perspective, the direction of magnetic field is supposed to be circular around the current carrying wire. So the thumb should be pointing into the screen. And if you draw the curl of the fingers, the curl of the finger is going to go like this. Your fingers will go like this. We are using right hand, not the left hand. Please make sure of this. So let's draw this in a better way. So what does so this is going to be the thumb, right? And these are going to be your fingers curling around like this, okay? So what is the direction of magnetic field that is going to come out here? So it comes out in this direction, like this. अच्छा, यही काम अब नीचे के लिए भी होगा, क्योंकि right hand grip rule तो वैसे ही लगना है. So it is going to be in this direction and then it's in this direction. तो अब जरा गौर से देखें हो क्या रहा है यहाँ पे. अगर आप वैसे इसको, उस कॉन्सेप्ट को आपने याद भी किया होता ना, even if you had memorized that if there are two conductors like this, two parallel conductors like this, and if they're carrying current in the same direction, they attract each other. We have this from memory. So we can confirm this from memory as well, that they are carrying current, at least for this part. This is carrying current in this direction, carrying current in this direction, looking at the green arrow. So they should be attracting each other, right? But let's figure that out in terms of magnetic fields. So over here, the magnetic field is towards that side. This causes to be this side. So the magnetic field is weaker. But on the outside, we can see that the magnetic field loop is completing like this. So the magnetic field on the outside is stronger and the inside it is weaker, which is why the magnetic force is always exerted from a region of strong magnetic field towards a region of weak magnetic field. So there will be a force on them which is going to attract them, which is going to bring them closer. Now let's try to apply the same thing will apply at this location as well. Be advised, this will happen exactly the same on these edges as well. And not to mention, what about these edges? The current was moving in this direction. What about the circular direction of magnetic field like here? And what about the magnetic field over here? What about the magnetic field over here? So it's going to happen at every single joint, but we can't draw that over here. It's not feasible. Now let's try. Let's apply the Fleming's left-hand rule. Now Fleming's left-hand rule requires that there needs to be a magnetic field. So if I am observing the first conductor, then I have to remove its magnetic field because it will be influenced by the second magnetic field, by the second conductor's magnetic field, right? Let's do that. Okay, so I am figuring out the direction of force on this conductor. Okay, so the direction of current or the direction of magnetic field experienced by this conductor is in this direction, as mentioned by this arrow. The direction of current because of this green arrow looks like this to me. Into the page, the thumb opens up in the downward direction. The force is experienced downwards. And if you were to draw this from this perspective, it would have come upwards. So all these ideas, all these things are pointing to just one direction. That is that this will contract. They are attracting each other. So now we know why it's happening. So we're just going to write down generic answer, generic statements that there is a magnetic field in the coil, right? Generic, very generic answer. There is a magnetic field in the coil which interacts with the magnetic field of adjacent loop. This is what we did, right? So we found the influence of this conductor due to this and this conductor due to this. So the adjacent coil's magnetic field is interacting with the current or the magnetic field of the first conductor. So interacts with the magnetic field adjacent loop. Okay, fine. They experience a force perpendicular to the direction of current and magnetic field. Again, this is a generic statement. It is just a simple implementation of the Faraday's law, right? Because what we did over here, we applied the Fleming's left-hand rule. We said that if, let's say, this is the direction of magnetic field, this is the direction of current, what is this plane? If you visualize, this is actually the same plane, or they exist in the same plane in 2 dimensions. And if you look at the 3rd dimension, which was the force, so that exists in the 2nd dimension, right? So, or you can say they're perpendicular to both of them. This is what this statement actually means in the marking scheme. So just memorize it, okay? And of course, we have to state whether it contracts or repels or extends. So this actually contracts. So it says when switch B is closed, the small mass in the free end of the spring is now made to oscillate vertically. Use the principle of electromagnetic induction, fluctuations in the current in the spring are found to occur. Why is this happening? So what's going to happen as this is going to vertically oscillate, for example, if this is what happens, if this vertically oscillates, then just look at this one conductor. What is this one conductor going to experience? Now, since this is contracting, this is coming close to it, and this is also coming close to it. So are they carrying some current in the wires? Yes, they are carrying current in the wires. So since this is coming close to this loop of wire, this loop of wire will experience a changing magnetic field due to the movement of this. You can experience it in this way. If you had a coil, you had a magnet far away, you bring it close and then you bring it back. When you do that, you're changing the magnetic field, although the magnetic field itself of the magnet is not changing, just because its vicinity, its closeness to you is changing. That means that the magnetic field is changing. And if there is a change in magnetic field, there will be an induced EMF in the coil. right? This is what he wants you to write down over here in generic statement format. You can write this down as well. So what does the oscillation cause? What have the oscillations done? Oscillations cause the change in magnetic field in the adjacent coil or experienced by the adjacent coils. This change in magnetic field caused an induced EMF in the coil, right? And this induced EMF caused an induced current in the coil as the magnetic field was cutting the coils. Simple. Okay. Question number 10. This is from Power, RMS, and that respective chapter. Okay. So let's figure this out. So this is, he says, by reference to the effect explained root mean square value of an alternating. What is the meaning of heating effect? So this is the definition of RMS current or RMS values, that such a value of direct current that produces the same heating effect as an alternating current would do. RMS बनाने का मकसद ये था कि हम ऑल्टरनेटिंग वोल्टेज को बार बार नहीं चेक करना चाहते, हम ये बार बार नहीं कर सकते, हम एक एक टाइम एक एक सेकंड पे बार बार वोल्टेज चेक नहीं कर सकते. आप हमें एवरेज वैल्यू बता दें जिसकी बेस पे हम ये सवाल सॉल्व कर लें. सो दिस इज द मेन पर्पस ऑफ आरएमएस. एंड ऑफ कोर्स अगर हमने एक मीन एवरेज वैल्यू निकाली है तो जितनी पावर एसी ने डिलीवर करनी थी उतनी ही पावर उसको भी डिलीवर करके दिखानी चाहिए, अदरवाइज कैलकुलेशंस गलत हो जाएंगे. ठीक है. ओके. सो दिस इज द करंट गिवन टू यू, राइट. ये साइनोसाइडल वेव है हमारे पास, एंड दिस इज अ स्क्वायर वेव. बाय द वे पुअर क्वालिटी यूपीएस जो उसकी आउटपुट होती है वो ऐसी होती है. दीज आर बोथ ऑल्टरनेटिंग. व्हाई? बिकॉज एक डेफिनेट साइकिल है हमारे पास, एक पीरियोडिक फंक्शन है, दूसरा एक पॉजिटिव भी है नेगेटिव भी है. ठीक है. ओके. So figure 10.1 determine the value of RMS and I1. Okay, fine. So 10.1 के लिए अगर हम देखें peak value is 2.6. So 2.6 यहाँ पर, this is 2.6. तो अगर आप यहाँ पर देखें, so this is going to be 2.6 is going to be the peak value, and dividing this with under root 2 gives me the standard RMS value, which is going to be 1.8 amperes. For 10.2 we'll have to figure it out in terms of visual cue at least. RMS बता दें, peak बता दें. peak value तो निकालना बहुत आसान काम है. यहाँ पे peak value हमारे पास 2 है. ठीक है. तो यहाँ पे 2.0 पीक वैल्यू आ जाएगी. बट व्हाट अबाउट द आरएमएस? देखिए आरएमएस बनाया क्यों था? आरएमएस इसलिए बनाया था ताकि हमारे पास नेगेटिव और जीरो आंसर ना आए. ठीक है. हमने पहले इस पूरे ग्राफ का किया स्क्वायर किया, तो ये नेगेटिव ग्राफ भी कैसे बन गया? पॉजिटिव. अब एक प्रॉब्लम है, स्क्वायर करेंगे तो वैल्यू तो ज़्यादा आ जाएगी. ठीक है. द वैल्यू विल इंक्रीज. सो 2.6 का स्क्वायर करोगे तो इतना बड़ा आंसर आएगा. सो ये पीक्स बड़ी बड़ी आ गई हमारे पास. बट एक फायदा क्या हुआ? द बेनिफिट वॉज दैट दिस नेगेटिव एक्सिस हैज बीन कन्वर्टेड इनटू पॉजिटिव एक्सिस. नाउ टू काउंटर दिस व्हाट वी गोइंग टू डू, वी गोइंग टू टेक द अंडर रूट अगेन. पहले खुद ही स्क्वायर किया, खुद ही अंडर रूट ले लिया, और फायदा क्या हो गया अब इस चीज का? दैट दिस होल ग्राफ इज गोइंग टू लुक समथिंग लाइक दिस. द होल ग्राफ इज गोइंग टू लुक लाइक अ पॉजिटिव ग्राफ लाइक दिस, राइट? एंड देन the area of that graph, the whole graph, was divided on a certain time period t. Then you get the RMS value. ठीक है. So if you were to do this job on this square wave, it will have no purpose. It will have no benefit. क्यों? Right now, for the sake of example, let's say that this is the area, and this is time t1, this is time t2, this is 3, this is 4. So if you were to take a square of this would have become 4. ये भी 2 पर है, -2 पे इसका स्क्वायर लेंगे तो 4 बन जाएगा. ये भी 4 पे आ जाता, ये भी 4 पे आ जाता, ये नेगेटिव से पॉजिटिव हो गया, ये भी 4 पे आ जाता. बाद में इसका अंडर रूट लेते तो क्या आता आपके पास? दोबारा 2 आ जाता. बट आफ्टर टेकिंग द अंडर रूट यू वुड हैव रियलाइज्ड दैट ये सारे का सारा ग्राफ सिर्फ पॉजिटिव बना है और तो कोई फर्क नहीं पड़ा. ठीक है. सो यू सक्सेसफुली कन्वर्टेड द होल ग्राफ इनटू द पॉजिटिव एक्सिस. सो दिस वुड हैव बीन द ग्राफ लाइक दिस. सारे का सारा ग्राफ पॉजिटिव एक्सिस में आ जाता. और अगर आप इसका एरिया निकाल के टी पे डिवाइड कर भी देते टू फाइंड आउट द एवरेज, तो टोटल एरिया दोबारा निकाल के दोबारा उसी पे डिवाइड करते तो दोबारा ये बन जाना था, ठीक है। तो इसीलिए इसकी स्क्वायर वेव की आरएमएस के अंदर कोई फर्क नहीं पड़ता, वो वही होती है जो उसकी पीक वैल्यू होती है। इसके ऊपर आरएमएस कैलकुलेट करने का कोई फायदा नहीं होता, क्योंकि हमें एवरेज वैल्यू चाहिए होती है ना। स्क्वायर वेव के लिए तो एवरेज वैल्यू का कॉन्सेप्ट ही कोई नहीं है, क्योंकि हर जगह पे है ही कांस्टेंट। हम चाहे जिस मर्जी रीजन में देख लें, इस रीजन में देख लो वैल्यू 2 वोल्ट है, इस रीजन में देख लो 2 वोल्ट है, वो चेंज नहीं हो रही। क्योंकि इसमें चेंज नहीं है, बिकॉज देयर इज नो वेरिएबिलिटी। हमारे पास ये गारंटी है कि मैं जिंदगी में जिस मर्जी टाइम पे भी चेक करूंगा ना, मुझे पता है वोल्टेज का आंसर क्या होगा। यहां पर प्रॉब्लम यह है कि हर टाइम पे हर इंस्टेंट पे वैल्यू चेंज हो रही है, जिसके लिए हमने एक एवरेज का कॉन्सेप्ट बनाया था कि भाई हम ये काम रोज रोज नहीं कर सकते, वी कांट चेक द वैल्यूज एट एवरी टाइम इंस्टेंट अगेन एंड अगेन, सो प्लीज कन्वर्ट दिस इनटू स्टैंडर्ड एवरेज वैल्यू व्हिच इज द आरएमएस। कहते जी मेरे पास एक्सप्रेशन है और हमें पता है कि एक्सप्रेशन इज एक्चुअली इक्वल टू वी नॉट साइन ऑफ ओमेगा टी। तो उसने हमें 50 सप्लाई बता दी, उसने कहा जी के निकाल दें, कोई मसला नहीं। सो वी नो दैट ओमेगा इज इक्वल टू 2 पाई एफ विच इज इक्वल टू के एज compared with the variables of the equation. So this is going to be 2 pi into 50. तो k मेरे पास जो निकल आएगा that will be 314 radians per second, but अगर इसको मैं 2 significant figure में लिखूंगा जो कि उसने मुझे कहा है सवाल में, so this is going to become 310. The supply voltage is applied to the heater. The mean power is 3.2. Calculate the resistance of the heater. Very easy. So we have the peak voltage probably. Yes, that is V naught. Peak voltage is V naught. So we need to find the resistance. So we can use the formula P equals to V square over R. उसने अगर mean power दी हुई है तो फिर आपको voltage भी RMS वाली ही use करनी पड़ेगी. So this is going to become 3200 equals to V RMS, which is going to be 240 divided by under root 2 divided by R. इसका whole square करना पड़ेगा आपको. So change their positions, perform correct algebra, and you will land on this answer as 9.03 ohms, which is going to become 9.0 ohms. Question number 11 हमारे पास है. Question number 11, CT scan. इसके तो बेटा I would recommend answer को बस memorize कर लें, रट्टा लगा लें, इसमें कोई ऐसा मसला नहीं है. So state the purpose of computerized CT scan. So we want to obtain the 3D image of the body. This is the only purpose it has. 3D image of the body. Outline the principle of CT scan. X-ray और CT scan में क्या फ़र्क होता है? X-ray is just unidirectional, right? आपने एक इमेज ले ली. CT scan में हम क्या करते हैं कि हम मल्टीपल डायरेक्शन से बार बार एक्सरे करते हैं ताकि ऑब्जेक्ट की 3D इमेज बन जाए. बस इतना सा फ़र्क है दोनों में. सो ये सबसे पहले तो बात करेंगे कि ये भी एक्सरे ही है, बट टेकन फ्रॉम many different angles to obtain the image of different slices which are in 2D. ठीक है, and this will be repeated of course for many different angles, right? So each 2D slice is combined by the computer to make a 3D image of that human body or that body that you're testing. इसका डेफिनेट सा आंसर है, याद करने वाली चीज़ है, कोई मसले वाली मसला कोई प्रॉब्लम, देयर इज नो प्रॉब्लम विद दिस, यू हैव टू मेमोराइज द आंसर्स. State what is meant by photon. So a quantum or packet of energy, but किसका, for whom? Packet of energy of electromagnetic radiation, which is starts from gamma, goes to radio, right? Okay जी. So we have gamma ray photon energy इतनी है, determine the wavelength. No problem. We have the formula of E equals to hc by lambda. Energy is given, we will replace it over here. So this is going to be 0.57 mega, so 10 raised to power 6 into 1.6 into 10 raised to power minus 19. That is a electron joules per electron volt. H is 6.63 Planck's constant as minus 34. C is 3 into 10 raised to power 8. Lambda can be found. Lambda is equal to 2.18 into 10 raised to power minus 12. So this will be 2.2 into 10 raised to power minus 12 or picometers. The momentum. So we need to use de Broglie's wavelength, which is lambda equals to h by p. So let's replace them. So p is equal to h by lambda. which is going to be equal to 6.63 into 10 raised to power minus 34. Equation याद करनी पड़ती है आपको. You have to memorize this equation. ठीक है ना? So this is going to come out as simply being divided by 2.2 into 10 raised to power minus 12. So momentum will come out as 3.0 into 10 raised to power minus 22 Newton seconds. So this is 3.0 into 10 raised to power minus 22. He says determine the speed of samarium 157. So isme we will have to use the momentum principle. We can assume that the nucleus of samarium, let's say, was stationary before. And now if it releases a gamma photon, the gamma photon is moving towards this side, the remaining samarium nucleus should move towards this side. And we understand that if this is the momentum of the gamma photon, it is moving at the speed of light. Okay, but anyways, the momentum of gamma should be equal to the momentum of samarium. Or you can say that if both are added together, the answer should be 0 because they're both moving in the opposite direction. Or you can say they must move in the opposite direction to conserve the momentum because इसके निकलने से पहले gamma निकलने से पहले तो momentum 0 था नहीं अपनी जगह पे पड़ा हुआ था. It was stationary on its own position. If today it is moving, for example, if it has released or kicked a gamma radiation on the outside, it should move on the opposite side so that it can have a negative momentum. This has a positive momentum. इन दोनों को add करेंगे. Adding both of them together should give me a 0 momentum because momentum before explosion should be equal to momentum after explosion. Okay. So moving on to this idea. So we have calculated the momentum of the gamma photon, which was previously 3 power minus 22. So this will be 3 into 10 raised to power minus 22. Velocity is what we need to find out. So वो वैसे ही आ जाएगी. And let's calculate the mass of samarium. This is interesting. पहले बताया बस देखें 157 is proton and neutron combined, right? So simply take 157 number of atoms or participants into the atomic mass unit, which is 1.66 into 10 raised to the power minus 27. We know that every proton and neutron inside the nucleus actually measures this much. It's only when they come out we realize that they are different. So then multiply this and carefully take it over there, that side, and do the algebra. You will find that the answer comes out as 1156. So this is 1156 meters per second. So this will become 1200 meters per second. Then he says, in reference to your answer to C1, यानी इसके बारे में बात करें, discuss about this. Quantitatively, right? Quantitatively means you have to refer to values. If it had been qualitative, it would have been just theory. Why the speed of samarium may be assumed to be negligible as compared to speed of gamma photon. You see, gamma photon or the photon, you will write down that the gamma photon is moving at the speed of light. You have to state, ये लिखना पड़ेगा आपको, at 3 into 10 to the power 8 meter per second, so that he knows that your knowledge is correct, right? And the speed 1200 meter per second is much less than 3 into 10 to the power 8 meter per second. Hence, it's considered negligible, right? तो आपने एक ये वैल्यू बताई और फिर कंपेयर किया. Then you compared them both after stating both values that this is negligible. It doesn't matter, right? Okay. So I hope that we understand this paper as well.